On a clear night, far from any city, the sky feels like it has no ceiling. Above you, the Milky Way spills across the darkness, a soft band of light that looks endless. Your eyes tell you that if you could just keep going, star after star would appear without limit. Yet the cold instruments we have lifted above the air say something else. They say your universe, the one you can ever see or test, is not endless at all. It is a bubble. Imagine that bubble as a sphere of light with you at its center. Every direction you look, every patch of sky you photograph, fits inside that sphere. It is not centered on Earth because we are special. It is centered on you because light has had just enough time to travel from that distance to your eyes. Beyond that shell, beyond that limit, set by the age of the cosmos and the speed of light, reality may go on, but its signals will never arrive. This is the quiet paradox. The universe itself may have no edge, no outside, no wall you could ever touch. But your universe, the one defined by the signals that can reach you, has a very real border. In every direction, there is a last possible galaxy, a last possible flash, a last possible whisper that could ever appear in your sky. Past that, there is not nothing, but there is silence that will never break. We did not discover this with poetry. We discovered it with glass and metal. A mirror in orbit collects faint starlight and sends it to a camera. A radio dish listens to a soft hiss that fills the entire sky. A detector cooled to a fraction of a degree above absolute zero counts rare particles arriving from space. When we turn those results into maps, the same strange shape appears again and again. Not a flat plane, not an infinite grid, a ball. The skin of that ball is what physicists call a horizon. Not a solid horizon like the crust of a planet, but a horizon of information. It marks the farthest distance from which light has had time to reach us since the beginning of cosmic time. There may be galaxies beyond that, full of stars and worlds and storms. There may be regions where matter is arranged in ways we have not even imagined. Yet for us, they might as well not exist, because nothing they do can cross the gulf. So the big question arrives, as quietly as a breath under the stars. If the universe has no outer shell, why does your view of it end? If there is more reality beyond the ball of light you inhabit, what does it even mean to talk about it, when you will never see a single photon from that realm? If this cosmic riddle speaks to you, please like and subscribe to the Quiet Universe channel to feel how strange this really is. Let us build a picture you can carry in your mind. Picture an island in a dark ocean. There is a tower on that island, made of stone at the base, then steel, then glass, then finally a narrow spine of instruments pointing upward. At the top of the tower stands a watcher. This is us, all of us, gathered into one figure. Every time we build a new telescope or detector, we add another floor to that tower and climb a little higher. From low on the tower, the watcher sees only nearby waves and a few faint lights on the horizon. From the middle, more lights appear, scattered across the water like distant ships. From very high up, the view changes again. What seemed like random points become chains and arcs, clusters and great filaments stretching off into the distance. The watcher realizes that the ocean is full of islands, full of distant ports of light. For a while, it feels as if this will never end. Each new floor reveals more structure, more detail, more of the grand design. But there is a surprise waiting. At some height, the horizon stops moving. The watcher climbs another floor and another. Yet the line where the sea meets the sky stays fixed. Beyond it, nothing new appears. The world seems to be wrapped in a soft shell, beyond which there is only perfect black. That is your situation as a species. The tower is your observatory, built over centuries. The ocean is space. The distant lights are galaxies. The horizon that refuses to move is the limit set by light and time. You can get better cameras, sharper mirrors, more careful clocks. You can learn to see every color of light, from radio waves to gamma rays. You can even use gravity itself as a kind of lens. Still, there will always be a farthest distance from which any event can ever affect you. In everyday language, you can think of this as the largest possible postcard collection. Every star, every galaxy, every flare that can send you a message is like a postcard written on light and carried through space. The longer the universe has been around, the farther those postcards can travel. But the mail does not move faster than the speed of light. There is a maximum distance from which a postcard could have arrived by now. All of your knowledge of the cosmos comes from the cards that made it in time. Now turn the picture around. Instead of asking how far the postcards have come, ask how far your own messages can go. If you were to send a signal, any signal at all, to the rest of the universe, how much of it could ever hear you? The answer is cruelly simple. Only those regions that share your bubble of light. Beyond that limit, even if they contain minds and machines of their own, your signal will never arrive. In their sky, you will never rise. Already, this should make you uneasy. When you say universe, what do you mean? Do you mean the entire structure of space and time, whether or not you can see it? Or do you mean the bubble defined by your own reach? The all that you can, even in principle, test. It is easy to slide between these meanings without noticing, yet the difference is the heart of the paradox. Most of us carry a simple picture in our heads. We imagine the universe as a ball floating in a larger, empty container. We put stars and galaxies inside the ball, and outside we leave a blank. We tell ourselves that if we had enough time and technology, we could fly and fly until we reach the outer surface, then either bounce off or cross into some other medium. Maybe vacuum becomes something thicker, maybe space breaks down, maybe there is a visible wall. But space as physics describes it is not a ball in a box. It is the box. There is no separate room for it to sit in. There is no direction in which you can fly that takes you outside of space. When we solve the equations that describe gravity and expansion, the results do not require an outer shell. They only require that distances between points inside space can change over time. This leads to a more careful question. If there is no outer wall in the usual sense, can there still be some kind of edge that matters? The answer, at least so far, is yes. There can be horizons that mark the limits of what any observer can ever access. These are not edges of existence, they are edges of experience. On your island, in your watchtower, those horizons are invisible. The sky does not show a ring that says beyond here, no more. What you see is a smooth distribution of light that becomes fainter with distance. Some galaxies are so far away that they appear as tiny red smudges. Their light has been stretched on its journey, thinned out by the expansion of space. Past a certain point, the smudges vanish, not because the galaxies stop existing, but because their light is too stretched and faint to register in any detector you could realistically build. Layer on top of that the fact that the expansion of space itself may be speeding up. Regions of the universe that are already far away are being carried off even faster as time goes on. A day will come, in the natural future of a universe like ours, when most of the galaxies you can see now will be gone from every sky that will ever follow. Their light will fade beyond detection. Their gravity will no longer bind to your own small cluster of stars. In a sense that matters to any future mind, those realms will fall off the map. If that is true, then you live in a rare kind of age. You exist in an era when the universe has had time to form stars and planets and life, but not yet so much time that the grand pattern has faded into a nearly featureless dark. Under your sky, the cosmic web is still visible. You can still see far enough to guess how it all began. You can still catch the faint afterglow of the early fireball, stretched into microwaves that hiss around you from every direction. It will not always be so. Picture an astronomer living hundreds of billions of years from now, far beyond any human future, in a small, lonely galaxy. That astronomer will look up and see almost nothing beyond their own local group of stars. No cosmic web, no background glow, no pattern of distant clusters to suggest that space is filled with matter, based only on what they can see. What kind of universe will they describe? How wrong would their picture be compared to yours? The thought should make you cautious. It suggests that our current understanding, as powerful as it feels, might still be a local story told from a very particular time and place. We like to say that the laws of nature are universal. Perhaps they are. But the parts of the universe those laws allow us to see may be a small and biased sample. We may be like a person staring out through a small round window in a vast building, insisting that the whole structure must look exactly like the view from that one pane. This is where the idea of the other side begins to change. It is no longer just a question about what lies past a physical edge. It becomes a question about what lies beyond our possible knowledge. There could be regions of space forever cut off from us, not because they are inside a wall, but because the rules of time and light forbid communication between us and them. For us, that boundary functions like an edge, even if for the universe as a whole, no such wall exists. And yet, human minds do not stop at that line. We imagine beyond it. We talk about infinite space, about repeating patterns, about other domains with different properties, about hidden layers of reality. We draw diagrams and invent terms. We write equations that extend beyond what we can observe, and then argue about whether those extensions describe anything real. Are we reaching toward a genuine other side? Or are we projecting shadows onto the inside of our own light cage? In the tower on the island, the watcher has two choices. They can treat the horizon as the end of the world and focus only on the islands within sight, or they can treat the horizon as a clue, a sign that there is more than they can see, and try to infer what that more might be from the patterns inside their own view. We have made the second choice. Cosmology, in its most ambitious form, is an attempt to read the entire story of reality from the small portion written on the bubble around us. That is why the paradox at the start of this film matters. It is more than a curiosity about how far away galaxies are. It is a test of how deeply we can trust our own picture. If our horizon is just a temporary limit, and the unseen rest is roughly similar to the part we know, then our theories may reach much further than our light. If, instead, the unseen rest is wildly different, or structured in layers we can scarcely imagine, then our theories may only describe one room in a far larger house. In the chapters ahead, we will push on this from several sides. We will follow the first faint starlight back toward the beginning, to see how the bubble grew. We will trace the way expansion bends distance and time, until even light cannot keep up. We will ask whether space might curve around and lead back to itself, turning the idea of an edge into something stranger. We will explore more daring ideas about other domains of reality, and ask what it would mean for our tiny bubble if they existed. For now, keep one image close. You stand at the top of the watchtower on your small island in the dark. Around you, an invisible sphere glows with all the light that has had time to reach you. Beyond that sphere is a region you will never see. The question is not only what lies in that unseen region. The question is what your brief, fragile life inside the bubble should mean. Once you know that most of reality, whatever it is, will never return your gaze. In the next chapter, we will step inside this light cage and begin to measure its walls from within. From the top of the watchtower, the sky seems calm. The stars drift across the darkness with the slow grace of ancient fires. And nothing in that view suggests that you are enclosed. Yet every telescope ever lifted above the atmosphere insists that you are. The universe you can study is not a boundless plane. It is a cage, shaped not by walls you can touch, but by light that has just barely had time to reach you. This chapter is about stepping inside that cage, measuring its boundaries from within, and learning what those boundaries truly mean. Begin with what you can actually see. A long exposure of the deep sky reveals hundreds of galaxies, each one a swarm of billions of stars. They look like scattered jewels. Some spiral, Some glow like diffuse ghosts. Some appear as thin slivers tipped in fire. The deeper the exposure, the more of them crowd into the frame. It creates the illusion that if you could simply stare longer or build a better lens, the sky would keep giving you more. But the illusion is only half true. At some point, the light becomes too stretched, too faint, too delayed to ever show itself. That limit is not technical. It is physical. It is the edge of your light cage. The idea is simple. Light travels at a finite speed. The universe has a finite age. Multiply these limits and you get a maximum distance from which light could have reached you by now. But expansion complicates this picture. Space has been stretching since the beginning. So the most distant light you can see today did not start from the static edge of a frozen sphere. It started much closer, then rode the expanding fabric outward while traveling toward you. By the time it arrives, the region it came from has drifted far away. This is why the radius of your light cage is far larger than the age of the universe in light years would suggest. The cage is not a clean geometric shell. It is a record of light-fighting expansion for billions of years. Look at that record more closely. The nearest entries are crisp, stars with sharp edges, galaxies with defined arms. We can resolve their clusters and even trace the arcs of their tidal interactions. Farther out, the details blur. The galaxies look smaller and redder, their light stretched by the expansion of space. Go farther still, and you find a fog. It is not dust. It is time itself. The early universe was hot and opaque, full of charged particles scattering light in every direction. When the universe cooled enough for atoms to form, the fog lifted and photons could travel freely. Those photons now wash over you as a background glow. They are the oldest light you will ever see. They mark the inner surface of your light cage, a kind of fossil horizon showing the universe as it was when it first became transparent. Pause and picture this. You are standing in a sphere defined by photons that have been traveling almost since the beginning. Everything you observe in space is built from these scattered messengers. They are your only contact with the outside world. You do not see galaxies as they are. You see galaxies as they were, filtered through the long war between gravity and expansion. The cage is not limiting your movement through space. It is limiting your access to the past. Now consider a detail that seems small but carries vast meaning. The farther away a galaxy is, the older the image you see. At modest distances, the delay is only a few million years. At extreme distances, the delay approaches the age of the universe itself. You can look deep enough to see galaxies assembling shortly after the first stars ignited. You can look even deeper and find the soft microwave glow, a cooled remnant of a universe still young and uniform. But there is a limit beyond which the past becomes inaccessible. Before the universe cooled and became transparent, no light could travel. That inner boundary is built into the physics. It is the first wall of your cage. But the outer wall is stranger. It is not a wall of fog. It is a wall of silence. There are regions so far away that their light will never reach you. Not because it is blocked, but because the expansion of space stretches that light faster than it can travel. Those regions exist. They have structure. They evolve. But your light cage excludes them completely. Their stories never reach the island where your watchtower stands. So here is the contradiction that drives this chapter. The universe reveals itself as vast, structured, and uniform. Yet the very laws that shape it tell you that your picture is unavoidably incomplete. The light cage gives you a beautiful but partial view. It shows you only the slice of reality whose signals can cross the gap. You can measure the cage, but you cannot escape it. Ask yourself, what does it mean to describe a universe when you can only see a fraction of it? What does it mean to build theories, to write equations, to imagine the whole structure? When your data comes from a shell of light surrounding a single point, if the unseen portion is similar to what you observe, then your theories might extend farther than your senses. But if the unseen portion is different in some crucial way, how would you ever know? How would your model adjust to a region whose signals can never reach you? Now bring this down to something simple. Think of a lighthouse on a foggy coast. The beam sweeps through the dark, reaching ships at some distances, but not others. A sailor far away might never know the lighthouse exists. A sailor close by might think the beam covers the whole world. Both sailors are wrong. The truth depends on where you stand. Your position sets your perspective. In the same way, your position in cosmic time and cosmic expansion sets the boundaries of your knowledge. This is why measuring the light cage is an act of humility as well as science. You are not mapping the entire universe. You are mapping the reachable universe. You are tracing the oldest and faintest photons that have chosen your island as their destination. Their arrival is not a sign that nothing exists beyond them. It is a sign that this is the maximum distance from which information has had time to reach you. This distinction matters. When we say the observable universe has a radius of roughly 46 billion light-years, we are not saying the whole universe is that size. We are saying that is the size of your cage today. Tomorrow it will be larger, because new photons from slightly farther regions will arrive. But in a distant future ruled by accelerating expansion, parts of the universe that are visible now will fade beyond reach forever. The cage grows and shrinks at the same time, depending on whether you follow the past or the future. Consider how strange this is. You live at a moment when the cage contains a rich tapestry of galaxies and structure. You can see clusters, filaments, and voids stretching across billions of light-years. But future observers will not be so lucky. As expansion carries galaxies beyond the reach of new photons, their skies will empty. Their light cage will contain only a tiny remnant of the universe you know. They might conclude that the universe is static and small, because that is all their data would show. They would be wrong, not by poor reasoning, but by poor access. Here lies a deep meaning. The universe does not present a stable picture to all observers at all times. The information flows, change with time. The cage shifts. What you can know depends on when you exist. This makes your current era remarkable. You are alive at a time when the cosmic web is still readable, when the early glow still touches your detectors, when the farthest galaxies still send their dying light to your world. This is a narrow window. It will not last forever. If knowledge itself has seasons, then you live in a season of abundance. That thought should change the way you look at the sky. When you observe distant galaxies, you are watching the last flickers of regions that may soon vanish from your cosmic horizon. When you listen to the background glow, you are hearing the soft echo of a moment that no longer exists. You are gathering messages that future worlds will never receive. So what does it mean to be inside this cage? It means you must learn to read the universe through the thin shell of light that reaches you. It means your models must account for the limits of observation as well as the structures you can see. It means that every answer you propose must carry a quiet warning that it describes only the reachable part of reality. And yet, this is enough. The cage does not trap your imagination. It frames it. By measuring the shell of light around you, you can infer far more than you observe. You can deduce the expansion of space, the age of the cosmos, the presence of dark components that shape the motion of galaxies. You can reconstruct the early fireball and predict the fate of distant clusters. Even inside the cage, the universe leaves clues. With these clues, we now turn deeper to see how the sky itself begins to change as parts of it drift away. The night sky looks calm, but that calm is a mask to the instruments perched on your world. The heavens are not fixed. They are sliding away. Their motion is not the motion of stars drifting inside a galaxy. It is space itself stretching. When space stretches, light thins. When light thins, the cosmos dims. If the stretching continues long enough, the very map of the universe you carry in your mind begins to dissolve. Begin again with what the watchtower sees. Imagine a deep field photograph, a patch of sky no wider than a grain of sand held at arm's length. That tiny patch contains thousands of galaxies. Some burn white, some glow red, some form arcs or smears, distorted by invisible mass. If you look only at the picture, it seems eternal. Yet every point in that picture is moving away from you as space expands. The expansion is smooth on large scales. It acts on every region at once, and it has been happening for billions of years. You might think that if everything is moving away, the universe would look uniformly dimmer, but the effect is more complex. Galaxies do not simply shift positions. Their light is stretched as it travels. Blue light becomes red. Red becomes infrared. Infrared slips into microwaves. The farther a galaxy is, the more this stretching dominates its appearance. It is as if the sky is painted on a great sheet that is slowly being pulled, making every mark on the canvas drift and fade. Now introduce a quiet but crucial idea. There are two horizons that shape your sky. One is the horizon of the past, the limit set by how far light has traveled since the beginning. The other is the horizon of the future, the limit set by how fast space expands. Beyond the first horizon, the universe is too young for light to have reached you. Beyond the second, the universe is expanding so quickly that new light from distant regions will never arrive. Between these horizons lies your season of visibility. This is where the contradiction sharpens. The deeper you look into space, the younger the universe appears. But there comes a distance where looking deeper does not reveal more. Instead of seeing new galaxies, you see a wall of silence. Not because something blocks the light, but because the universe is running away faster than the light can cross the gap. Your view into the past grows richer for a while, then stops. Meanwhile, your view into the future grows poorer as galaxies drift beyond reach. Think of this in human terms. Imagine you are standing on a long, straight road at dusk. Ahead of you are rows of streetlights. The ones close by are crisp and bright. The ones farther away are faint. Now imagine that the road beneath your feet begins to stretch. The streetlights do not move on their own, but the space between you and them increases. Each light grows dimmer, then vanishes. You can still see the ones nearby, but the far ones slip into darkness. If the stretching continues, even the lights that were once close will fade away. This is not a thought experiment. This is the fate of your sky. We already see galaxies whose light is stretched so severely that only the most sensitive detectors can register it. Their images are faint, red, and fleeting. They flicker on the edge of observability. As expansion accelerates, these galaxies will cross the horizon of the future. They will continue to exist. They will continue to evolve, but their light will never touch your world again. Here is where the mind stumbles. If the universe contains so many galaxies, why should the sky not remain rich forever? Why should it thin out? The answer lies in the rate of expansion. If the universe expanded at a steady or declining rate, then over time, more and more distant regions would send their light to you. Your visible universe would grow. But we have measured something different. We find that the expansion is accelerating. This means that distant regions speed away faster as time goes on. Their light stretches more and more. At some distance, the stretching wins. In everyday language, you can think of a ship sailing away from you across a dark sea. At first, you can see its lantern clearly. As it moves farther, the lantern is dimmer. If the ship slows or stops, the lantern remains in view. But if the ship accelerates quickly enough, the lantern vanishes. It is not that the lantern stops shining. It is that the waves reflecting its light can never reach you. Space behaves like that sea, except the ship is every distant galaxy and the acceleration is built into the geometry of space-time. This leads to a chilling consequence. As time passes, the sky you know today will not remain. One by one, distant galaxies will slip over the horizon of the future. Their last photons will reach you, then nothing more. Clusters that once glowed like embers on the cosmic web will fade into perfect darkness. Superclusters will vanish. Even the bright arcs used to map dark matter will thin out. Eventually, only the galaxies bound to your own small region will remain visible. Pause here. Let the weight of this settle. The cosmic web, with its elegant filaments and vast voids, is not a permanent feature of the sky. It is a temporary gift, a pattern that appears during a narrow chapter of cosmic history. You happen to live within that chapter. You happen to exist at a time when galaxies are still sending their light across the dark. That is not guaranteed. It is a cosmic stroke of luck that allows you to reconstruct the universe's story. This raises a haunting question. If a civilization arises in the distant future, long after the cosmic web has slipped beyond visibility, what will they conclude about the universe? With no evidence of distant galaxies, no map of large-scale structure, no background glow from the early fireball, their picture will be small. They may believe that the universe is static. They may believe it contains only one cluster of stars. They may never suspect that they are gazing into a sky that has lost almost everything. From this, a deeper meaning emerges. Knowledge is time-bound, not because intelligence changes, but because the universe does. Certain truths are visible only at certain stages. The expansion of space hides its own past. It erases clues as time passes. If you want to understand the universe, you must take advantage of the era you inhabit. Later eras may offer sharper instruments, but emptier skies. Now let us return to the watchtower. From its height, you can see how the sky shifts. The galaxies that appear as faint red smudges are the first to slip away. They sit near the edge of your current view. Their last photons are still arriving, stretched thin across the darkness. Soon they will drift across the future horizon. Then the galaxies nearer the middle distance will follow. Each step reduces the richness of the sky, until only the local islands of stars remain. Imagine that transformation as a slow dimming of a great cathedral ceiling. At first, the ceiling is washed in light from distant stained glass windows. Then some distant windows fade. Then more. Eventually, the ceiling is lit only by a few lamps close by. The architecture remains vast, but the illumination disappears. You could walk through the cathedral and never know how grand it once was. This slow emptying carries a simple question. What is the universe when the sky is nearly blank? Does the structure of reality remain meaningful when almost none of that structure can be observed? Can a theory of the cosmos survive when the evidence that once supported it can no longer reach any observer? We answer these questions by returning to what is visible now. The sky that is slipping away still holds the clues needed to understand its fate. We see galaxies receding at speeds proportional to their distances. We measure the rate of acceleration. We see the microwave afterglow stretched thin but still present. Together, these observations tell us that the loss of the sky is not arbitrary. It is the natural outcome of cosmic expansion and the dominance of a mysterious driver pushing space itself to grow more rapidly. Why does this matter? It matters because everything you know about the universe hinges on what remains visible. It matters because cosmic history is written in fading ink. It matters because if the sky thins, the archive of evidence thins with it. And it matters because without this expanding view, you would have no idea how the universe was born or how it evolves. Before we close this chapter, return once more to the human scale. Think of an old family album. Some pages are sharp and colorful. Others have faded photographs that barely show faces or places. The oldest photos may be so washed out that only shadows remain. Your view of the universe is like that album. The newer pages are clear. The older ones are pale. And some pages, which contained images of distant relatives in far-off places, are missing entirely. This is why the slipping sky is more than a cosmic curiosity. It is a reminder that the universe is not a fixed picture. It is a story in motion. And the parts of that story you can read depend on where you are in time. You live in a rare moment when the book is still open wide. In the next chapter, we will chase the earliest starlight before it fades entirely. At the edge of your fading sky, a fragile glow still survives. It is ancient, stretched thin, almost too faint to grasp. Yet inside that glow lives the story of how the cosmos first learned to shine. This chapter follows that path into the early darkness. It is a chase across time, guided by photons that began their journey long before Earth formed, long before the Milky Way spiraled into its present grace. To understand where the universe is going, we must learn what its first light looked like, what it carried, and why that light is slipping from our grasp. Begin with a simple picture. Imagine a vast ocean at night. Near the shore, lamps from distant ships sparkle across the water. Beneath that gentle shimmer, faint glints appear, deep below the surface, as if something far older is stirring. Those glints are the earliest stars. They shine from a time when the universe was young, when matter was gathering for the first time into knots dense enough to ignite nuclear fire. The photons those stars released have traveled through an expanding ocean of space for billions of years, stretched and cooled, until they reach your detectors as tiny flecks of infrared. You do not see these stars directly with your eyes. They hide in wavelengths your vision cannot detect. It takes a machine perched beyond Earth's glare to find them. A telescope with mirrors sculpted so finely that a single grain of sand would deform their perfect shape. That telescope reaches into the invisible red, where the ancient starlight now resides, and pulls from the darkness a record of the dawn side of cosmic time. Look at one of those early galaxies. It is small, chaotic, and irregular. It does not have the elegant spiral arms that define the galaxies of today. It is a crowded nursery where gas clouds collapse and ignite in bursts, where heavy elements are only beginning to form. The light from these stars is hot and blue when it leaves them. During its long flight across expanding space, that light is stretched into red. By the time it reaches you, it is almost unrecognizable. This stretching of light is more than a visual effect. It is a clue. It tells you how much the universe has expanded. It allows you to measure the speed at which distant galaxies are receding. It tells you how long the photons have been in flight. The deeper the red of the light, the more ancient the signal. By following these colors, you move backward in time toward the first generation of stars, the moment when matter learned to burn. Now picture the universe before those first stars appeared. There were no galaxies, no clusters, no planets, no suns. There was only dark matter, and gas spread thinly across space. The gas was mostly hydrogen, with a trace of helium and almost nothing else. It was a cosmos without structure, without heavy elements, without any of the ingredients that make stars long-lived and complex. In that early darkness, gravity gathered clouds of hydrogen into tight regions. Once the density crossed a threshold, the first stars ignited. These first stars were not like the ones you see today. They were enormous, many times more massive than the sun. They burned fiercely and briefly, exploding after only a few million years. Their explosions forged heavier elements, scattering them across space. Those elements became the seeds for later generations of stars and planets. Without those early giants, the universe could never have built carbon, oxygen, or any of the materials from which life eventually formed. The catch is that we do not see these first stars directly. They lived fast and died quickly, and their light is buried beneath billions of years of expansion. What we do see is the integrated glow of their descendants, the second generation of stars forming in the first galaxies. These early galaxies appear as dim red specks, barely detected even by the most sensitive infrared telescopes. They flicker at the boundary of observability, representing an era that is slipping away as expansion accelerates. So here is the contradiction at the heart of this chapter. The early universe contained the keys to everything that followed. It was the furnace in which the first light was forged. If we want to understand cosmic history, we must study that light. Yet the very expansion that carries its photons to us also pushes the sources beyond the horizon of the future. The more we learn, the more the window into that era narrows. Think of a long corridor lit by candles that burn out one by one as you travel. Behind you, darkness grows. Ahead of you, a few weak flames illuminate the walls. The more steps you take, the fewer lights remain. Eventually, the corridor will be fully dark. That corridor is cosmic time, and the candles are the distant galaxies, whose ancient light still reaches you. Each epoch pulls another flame beyond reach. What remains is precious. This is why astronomers chase the earliest starlight with such urgency. They are not merely cataloging distant galaxies. They are gathering the last surviving clues about how structure formed. They are measuring the temperature and texture of the early cosmos. They are catching photons that have crossed the longest distances possible within your light cage. Missing these photons means losing the ability to reconstruct the first chapters of cosmic evolution. In everyday language, think of the earliest starlight as the oldest page in a book. If that page is torn or faded, you may still understand the story, but your understanding will be incomplete. If that page is missing entirely, the story will begin in the wrong place. You would imagine explanations that are not true. The first page does not control the whole story, but it sets the foundation. Without it, you misread the rest. The challenge is that the page is disappearing. The faintest early galaxies are already at the edge of visibility. Their redshift is so extreme that only deep infrared instruments can detect them. Some are already beyond the horizon of the future. Their last photons are en route now. When those photons arrive, no more will follow. Their stories will end mid-sentence. This raises a haunting question. How much of the universe's true beginning will be forever sealed from us? How close can we get to the first generation of stars? Are we seeing the earliest versions of galaxies, or only the ones bright enough to survive the long journey to our world? And how many structures formed that we will never know existed? Even within these uncertainties, there is meaning. The universe has given us just enough clues to reconstruct the broad outline of its early evolution. We see that matter was gathered by gravity into filaments. We see that regions of slightly higher density grew faster, forming the seeds of galaxies. We see that light from early stars reionized the gas, ending the cosmic dark ages. We know that without this sequence, galaxies like the Milky Way would never have formed. And yet, the more distant the source, the more expansion distorts its message. Time stretches. Colors shift. The universe itself becomes a lens that filters and weakens the light. By the time the earliest starlight reaches us, it is less a picture and more a whisper, a fragile signal floating on the edge of detectability. Why does this matter? It matters because the early universe decides the shape of the later one. It matters because the first starlight encodes how structure grows. It matters because by understanding the dawn, we understand why galaxies form the way they do, why stars are born in clusters, why planets arise in disks of dust. It matters because without the earliest starlight, you cannot tell how the cosmic web blossomed into the pattern you see in the sky today. Now return to the human scale. Think of a memory from your own childhood, one preserved only by a faded photograph. The colors are weak. The edges blur. You recognize yourself, but only barely. The picture does not show the entire moment. It shows only what the camera captured, filtered by time and decay. Yet that one photograph carries meaning. It tells you where you came from. It shapes the story you tell about your own life. The earliest starlight is the universe's childhood photograph. It is imperfect. It is incomplete, but it is the only record of a time when everything you see today was being assembled. If we lose that light, we lose our deepest link to the origin of the cosmic web. As expansion accelerates, this chase becomes a race. The earliest galaxies are moving away faster and faster. Their light is stretched thinner each moment. We can still see them, for now. But the horizon of the future draws closer for each of them. To catch the full story of how the universe began, we must follow the faintest signals, the dying embers of the first fire. In the next chapter, we will follow those embers back to the moment when the universe outran itself, and space expanded faster than light could ever hope to cross. There is a moment in cosmic history that defies every ordinary intuition you carry. It is the moment when the universe expanded so quickly that parts of space were pulled away from each other faster than any signal could have crossed the gap. This was not motion through space. This was space growing between points that had barely existed. It happened when the universe was young, hot, and smooth, long before stars ignited or galaxies formed. This chapter traces that moment, the moment when the universe outran itself. Begin at the end of the previous chapter. You were chasing the first starlight, photons that traveled billions of years to reach your detectors. Those photons come from a time well after the event we explore here. As ancient as the first stars are, they are still children in comparison to the earliest chapters. The first stars appear hundreds of millions of years after the beginning. The moment the universe outran itself takes place a fraction of a second after the beginning, in a blink too short for any structure to form. Imagine standing inside an impossibly hot and dense fog. There are no atoms, no molecules, not even stable particles for more than fleeting instants. Everything is squeezed into a tiny volume, a primordial mixture of energy and fields. You might picture a bright, boiling surface, but there is no surface. There is no inside or outside. There is only a region of space that is about to become unimaginably larger. Within this region, something extraordinary happens. Space begins to stretch. Then it accelerates. And then, for a brief moment, the stretching becomes so intense that it tears apart causal connections faster than light can keep pace. To feel the strangeness of this, think of the universe as a blank sheet of fabric. If you pull the corners gently, the threads shift slowly. A ripple of motion spreads across the sheet at the speed allowed by the material. But if you grab the sheet and yank it outward violently, there is a moment when the distance between threads jumps before any ripple can cross the surface. The sheet expands faster than the signal that would tell the threads how far apart they have moved. The threads do not travel across the sheet. They are simply carried apart by the stretching. In everyday language, this is what physicists call a burst of rapid expansion. The expansion was not limited by the speed of light because nothing was moving through space. Space itself was stretching. The rules of relativity restrict how fast objects can move across space, not how fast space can grow. During this brief episode, tiny fluctuations in the early universe were blown up to cosmic scales. Smooth regions became smooth across immense distances. Small ripples became the seeds of galaxies. This event answers several deep questions. Why is the universe so uniform? Why does the cosmic background glow look almost identical in every direction? Why are distant regions, separated by vast stretches of space, so similar when no signal has had enough time to travel between them, without rapid expansion? These questions have no convincing answer. With it, they fall into place. Regions that are now separated were once close enough to share information. Expansion simply pulled them apart before their shared origins faded. But this explanation carries a contradiction. The moment the universe outran itself solves the problem of uniformity, but it also creates regions that are forever beyond contact. If expansion had been gentle, the universe might have remained a single, connected whole. But the burst of rapid growth carved it into domains that cannot communicate, even in principle. The light cage you inhabit is one such domain. Beyond it, there may be others, separated from you not by distance alone, but by the limits of causal structure. Think about that carefully. Even if the universe has no physical boundary, this early expansion creates effective boundaries. They are not walls of matter or energy. They are boundaries of causality. If two regions were pulled apart faster than light could keep up, then no signal, no matter how clever the device, can cross the gap. They will never share information again. They will never see each other. To each region, the other is beyond the horizon of the possible. This raises a profound question. If the universe outran itself once, could it still be doing so in other places? Could some regions continue to expand rapidly while others slow down? Could space be inflating in pockets, scattered across a larger structure? If so, our entire bubble of visibility may be just one piece of a much larger and more complex cosmos. Here is where the story takes a speculative turn, guided by mathematics and by the faint structures we observe in the sky. Some models of rapid expansion suggest that the burst never ended everywhere. Instead, it ended in our region, allowing stars and galaxies to form. But in other regions, it may have continued. Those regions would be expanding so swiftly that no light can reach from them to us. They would remain hidden forever, separate domains with their own internal histories. Picture a vast field of soap bubbles. Each bubble forms, grows, and then detaches from the foam. The bubbles do not collide because the foam between them expands faster than they can drift. Each bubble has its own interior landscape. Each contains a slice of the original material, stretched and shaped by internal processes. From inside any bubble, the others are invisible. Their surfaces move away faster than light can cross the gap. Your universe could be one such bubble, an island in a sea of expansion. If this picture is even partly correct, it changes the meaning of everything you call the universe. The horizon you face is not the boundary of space. It is the boundary of your bubble. Beyond it may lie other bubbles, or none at all, or a vast structure so different from your local region that your physical laws might not apply there. The moment the universe outran itself may have created not one cosmos, but many. Why should you take such a possibility seriously? Because the evidence that supports rapid expansion also hints that the process could have continued in ways we cannot see. The smoothness of the cosmic background glow, the distribution of galaxies, the overall geometry of space, these clues suggest that the early universe was driven by a field of energy that could, in principle, act unevenly across space, ending here, continuing there. Even if the details remain uncertain, the logic is difficult to ignore. But let us return to what you can observe. You do not see the early burst directly. You see its aftermath. You see the uniformity of the background glow. You see the patterns of tiny temperature variations in that glow. Those variations are fingerprints of the early ripples stretched by the rapid expansion. They tell you how much space grew, how smooth it became, and how the seeds of galaxies were planted. This is as close as you can get to the moment when space outran itself. At this point, a human-scale image can help. Think of a balloon being inflated. Small marks on the surface move apart as the balloon expands. If the balloon expands slowly, the marks remain close enough to compare. But if the balloon is blown up in a sudden burst, the marks on opposite sides end up far apart, far beyond the reach of any pattern you could draw between them. Now imagine that the balloon is not a surface but a volume. The burst of expansion pushes everything outward in all directions, stretching distances beyond what any signal could bridge. Why does this matter? It matters because the shape of the universe you observe today is written into those early conditions. It matters because the cosmic web began as tiny fluctuations amplified by rapid expansion. It matters because every galaxy, every cluster, every star owes its existence to the seeds planted in those early moments. It matters because the horizon you see now is a direct consequence of the limits imposed by that ancient burst. As you follow this chain of meaning, another question emerges. If the universe once expanded faster than signals could cross it, what does that say about the limits of knowledge? Could there be regions of space that share no history with ours? Could there be domains that formed under different conditions, inaccessible forever? If so, the concept of a single universe may be too narrow. What we call the universe may be only one chapter in a larger structure. This idea pushes against intuition. We are used to thinking of the universe as everything that exists. But if rapid expansion carved the cosmos into isolated regions, then everything that exists might be too large to observe, too varied to describe with one set of laws. We are left with a narrower definition, one based not on what exists, but on what is accessible. Return now to the watchtower. Imagine the watcher climbing to a new height, built by the discoveries of early expansion. From this vantage, the watcher sees not only the fading sky and the earliest starlight, but the shape of the universe's birth. The watcher sees that the cage of light around the island was shaped by forces that acted long before the first stars shone. The watcher sees that the island sits inside a bubble, a region defined by how far light can travel since that early burst. This view changes the way the watcher reads the sky. The galaxies that slip away are no longer just drifting islands. They are signals being stretched by a cosmic history that began with a violent expansion. The earliest starlight is no longer just a glow. It is a record of ripples amplified across unimaginable distances. And the horizon is no longer just a boundary of observation. It is a fossil of the moment when the universe outran itself. In the next chapter, we will measure the moving cosmos that carries these clues, and see how our rulers and clocks struggle to keep pace with a universe that refuses to slow. To measure the universe is to measure something that refuses to stay still. It is like trying to weigh a river that is always flowing, or to chart a shoreline while the tide rises beneath your feet. The cosmos is not a fixed stage where events play out. It is a restless structure that changes as you watch it. Distances stretch. Light thins. Time dilates. Every attempt to draw a clean map must contend with the fact that the map is printed on a surface that keeps drifting. In this chapter, we step inside that problem and ask what it means to measure a moving cosmos. Begin with the simplest tool, the idea of distance. On Earth, distance feels like something solid. A meter is a meter. A kilometer is a kilometer. You expect that if you return to a place after a year, the space between 2 points will not have changed. But in the universe at large, space is not fixed. If you choose 2 galaxies separated by a vast gulf, that gulf grows with time. The galaxies are not sailing through space like ships. The space between them expands. If you try to measure that distance directly, the measurement changes even as you make it. Think of a long wooden ruler placed on a floor. If the floor begins to stretch, the ruler no longer matches the surface. You mark a point, measure again, and find that the distance has changed. It is not that your ruler is wrong. It is that the floor is moving. Now imagine that the entire universe is that floor, stretching at every scale beyond the reach of gravity. Your ruler cannot capture it. Your clock cannot isolate it. You must look for indirect clues. Astronomers use light as a ruler. The color of light stretches as it travels through expanding space. Blue light moves toward red. Red moves into infrared. Infrared slips into microwaves. This shift is measurable. It tells you how much space stretched during the light's journey. The more the shift, the greater the expansion. Each galaxy becomes a marker. Its light carries a record of the path it followed, like a trail of breadcrumbs left by time itself. But this approach introduces a contradiction. If the light stretches because of expansion, then the distance you measure depends on how the universe changed during the journey. You cannot simply take the color shift and convert it into a single number. You must reconstruct the entire history of expansion from the beginning to now. The map you build relies on the very phenomenon you are trying to measure. This circular logic is not a flaw. It is a challenge. It requires a careful model of how space grows. Those models have evolved. Early attempts assumed a steady rate of expansion. Later measurements showed that the rate is changing. Today we know that the universe is expanding faster over time. This acceleration shapes your measurements. If the expansion were slowing, distant galaxies would appear closer than they do. Because the expansion is speeding up, they appear farther. Your ruler is not just stretched, it is stretched unevenly. Now consider the ladder used to measure cosmic distances. It is not a single method. It is a chain of methods stacked one atop another. At the bottom are parallax measurements, which use the motion of Earth around the Sun to triangulate the positions of nearby stars. Above that are variable stars whose brightness can be predicted. Above them are supernovae, explosions with nearly uniform luminosity. Each rung extends the reach of the previous one. Each rung carries uncertainties. This ladder is powerful. It allows you to measure out to galaxies millions and billions of light years away, but it is also fragile. If one rung is miscalibrated, the entire ladder leans. And in recent years, researchers have found a subtle inconsistency. When they use nearby stars and supernovae, they get one value for how fast the universe expands. When they use the background glow from the early universe, they get another. The disagreement is small in percentage, but large in meaning. It suggests that the map you draw may contain a hidden crack. Imagine again the ruler on the stretching floor. If you use a small section of the floor to make marks, you get one measurement. If you use a distant part of the floor, you get another. The difference might be telling you that your interpretation of the stretching is not complete. Perhaps the floor stretches differently in different eras. Perhaps your ruler shrank without you noticing. Or perhaps there is some deeper feature of the floor, an unseen pattern that distorts your readings. This disagreement has become one of the most intriguing puzzles in modern cosmology. It is as though two clocks that should agree insist on telling different times. If the universe is a single system with consistent rules, every path to the same measurement should converge. The fact that some do not suggest that something is missing. Maybe your model of how the universe expands needs an adjustment. Maybe space behaves differently at early times than at later ones. Maybe there is a subtle interaction you have not accounted for. To a mind trained to look for deeper meaning, this is not a failure. It is a clue. When a pattern breaks, something new is waiting beneath it. When a map shows a crack, the crack marks the place where to look next. The cosmos is telling you that your understanding is incomplete. The disagreement between different ladders is a signal that there is more structure to discover. Bring this down to a human scale. Imagine that you are surveying a coastline during a rising tide. You take measurements at dawn, noon, and dusk. At dawn, the tide is low, and you mark the line where the water meets the rocks. At noon, the tide is high, and your marks do not match your earlier ones. At dusk, the tide is falling, and your marks shift again. If you did not know the tide existed, you would think the coastline was unstable. Only by recognizing the pattern of rising and falling can you reconcile your measurements. The universe may be doing something similar. The expansion might be influenced by factors that vary over time. If you do not include them, your measurements will disagree. Light itself plays a role in this confusion. The farther away a galaxy is, the longer its light has traveled, and the more the universe has changed during its flight. You are not measuring distance at one moment. You are measuring an average over the entire journey. It is like trying to measure the length of a road while the road itself is being rebuilt. Your measurement reflects every change that occurred along the way. Despite these challenges, the methods work remarkably well. They reveal a universe that is nearly flat on large scales, meaning that its geometry resembles a sheet rather than a sphere or a saddle. They reveal that most of the energy in the universe exists in a form you do not understand, a form that drives the acceleration of expansion. They reveal that galaxies form in a web-like pattern. They allow you to infer the presence of invisible mass that shapes the motions of stars. Why does this matter? It matters because every measure you take shapes your understanding of the cosmos. It matters because even small disagreements hint at new physics. It matters because to explain the origin, you must know the pace of expansion. It matters because the pattern of growth decides how galaxies evolve, how clusters form, and how the cosmic web changes over time. It matters because if your distances are wrong, your story of the universe may need revision. Consider another human scale view. You are reading a map while walking on a treadmill. The map shows your position relative to landmarks, but the treadmill moves beneath your feet. Your steps do not carry you across the ground. The ground itself slides. If you use your footsteps to measure distance, your measurements will be off. Only by recognizing the motion of the treadmill can you correct your map. The universe is the treadmill. It moves beneath you. Your steps must be interpreted through its motion. Return now to the watchtower. The watcher stands atop the island, holding a set of rulers and clocks. the watcher marks the positions of distant galaxies, then returns a year later to check the marks. The marks have shifted, not because the watcher miscounted, but because the sky has changed. The watcher tries to draw lines between galaxies, but the lines bend as space expands. The watcher tries to capture the shape of the cosmic web, but the web is stretching. This shifting landscape forces the watcher to adopt new strategies. Instead of measuring distances directly, the watcher measures patterns. The watcher studies the way galaxies cluster. The watcher listens to the faint hum of the early universe. The watcher looks for the small fluctuations that betray the ancient seeds of structure. These patterns do not rely on fixed distances. They rely on relative scales. They provide anchors in a drifting world. With these tools, cosmologists build a model that describes the expansion from the earliest moments to the present. It is a model that accounts for light, matter, and the mysterious force driving acceleration. It matches many observations. But the tension in the measurements remains. It reminds you that the universe may not be as simple as the model suggests. It may contain surprises beyond your current reach. In the next chapter, we will ask whether space itself loops back around, turning the idea of distance into something stranger and challenging the very notion of a cosmic edge. Stand again atop the watchtower. The sky stretches in every direction, calm and deceptively simple. The stars form arcs that rise and fall in regular paths. Galaxies drift across the darkness as faint embers. Nothing in that view suggests a hidden loop. Nothing hints that if you could travel far enough in one direction, you might eventually return to your starting point without ever turning around. Yet this is one of the boldest questions in cosmology. Does space have a global shape that curls back on itself? Could the universe be finite but unbounded, like the surface of a sphere extended into 3 dimensions? Begin with something familiar. Imagine walking around Earth. If you set off from one point and walk straight without changing direction, you eventually come back to where you started. You do not encounter an edge. The world curves beneath your feet. From your perspective on the ground, the planet looks flat. The horizon looks like a circle. You do not feel the curvature. Only when you travel far enough does the looping nature of the surface reveal itself. Now extend that idea to 3-dimensional space. If space is curved in the right way, you could in principle travel through the cosmos in a straight line and return to your starting point. There would be no boundary, no outer wall, and no edge to fall off. The universe would be finite in volume but infinite in direction. It would be like living inside a vast labyrinth where every corridor eventually connects back to another, though you might never notice unless you trace the entire route. This possibility is not fiction. It is allowed by the equations that describe gravity and geometry. Those equations permit several global shapes for the universe. Space can be flat, meaning it stretches forever in every direction. Space can be open, meaning it curves outward, like a saddle. Or space can be closed, meaning it curves inward, like the surface of a sphere. In the closed case, the universe would have no edge, but it would fold back on itself. The challenge is simple to state, yet nearly impossible to overcome. How do you tell whether space loops if the region you can observe is limited by your light cage? Your visible universe is a sphere about 46 billion light-years in radius. If the actual universe is larger than that, you cannot see its full structure. If space loops only at scales beyond your visible region, there is no direct way to trace the loop. Every test you perform must be done inside your bubble. So scientists look for signs. One sign would be repetition. If space loops, light might wrap around the cosmos and return from the other side. You could see multiple images of the same galaxy in different directions. You could see repeating patterns in the cosmic background glow. You could detect echoes of distant events appearing in multiple parts of the sky. In a looping universe, the cosmos becomes a hall of mirrors. The images would be faint and distorted, but they would repeat. So far, no such repetitions have been observed. The cosmic background glow appears smooth and does not show matching circles that would betray a loop. Galaxies do not appear in duplicated positions. The structures we map seem unique. These clues suggest that if space does loop, the loop occurs at a scale larger than the visible region. The universe could still be finite, but the loop might lie far beyond the part of space from which light can reach you. Think of walking in a dense fog. The fog limits your vision to a few steps. If you walk in a circle, you will eventually return to where you began. But if your circle is larger than the range of your sight, you will never notice. Every direction looks the same. The path feels straight. The loop hides inside the fog. Your bubble of vision acts like that fog. You can see only the nearby region. If the loop lies beyond your horizon, you cannot detect it. This uncertainty reveals a deeper point. The global shape of the universe is not determined by local measurements alone. The region you inhabit is almost perfectly uniform and flat. But a flat region does not prove the whole structure is infinite. Earth appears flat on human scales. But that flatness does not imply an infinite plane. The curvature is too slight to feel. Similarly, space can be nearly flat inside your visible region and still loop on scales beyond your reach. Bring this idea down to something you can hold. Visualize a maze carved into a smooth landscape. The walls of the maze are low and distant. The path you walk seems to stretch in a straight line. You move forward for hours and never see a curve. Then one day, you discover you have returned to your starting point. The maze was laid out on a gentle slope that curved back around. The flatness you sensed was real but incomplete. Now return to the question at the heart of this chapter. Does space loop? The honest answer is that we do not know. The universe may be infinite. It may be finite but unbounded. It may have a complex shape that twists in ways our intuition cannot picture. The lack of repeating patterns in the sky tells us only one thing. If the universe loops, its loop is larger than the part we can observe. This is not just a geometric puzzle. It affects how we think about cosmic origins and cosmic fate. If the universe is infinite, then every possible arrangement of matter may occur somewhere. Patterns may repeat in distant regions. Entire structures may appear in multiple copies. But if the universe is finite and loops back on itself, the set of possible arrangements is limited. The story of matter becomes a closed book with a finite number of pages. Structure evolves, but the total space in which it evolves is fixed. Why does this matter? It matters because the shape of space influences everything that happens within it. It matters because whether space loops affects the possible distribution of galaxies. It matters because a looping universe could create global constraints on motion. It matters because knowing the shape helps define what kind of cosmos you inhabit. It matters because if the universe loops, there may be deep connections between regions you think are far apart. The idea of looping space also touches the question of cosmic origins. If the universe is finite and curved, it may have undergone cycles in ancient times, expanding and contracting in rhythms beyond our view. Some models suggest that rapid expansion could occur repeatedly in different regions. In such models, the universe becomes a dynamic, self-connected structure where beginnings and endings blur. To explore this further, think of a drum skin vibrating. The drum is finite, but the vibrations create patterns that fill the surface. The patterns repeat, overlap, and shift. If space behaves like a higher dimensional drum skin, the expansion and contraction could create echoes across the cosmos. These echoes would not be literal vibrations. They would be repeated sequences of growth and cooling influenced by the underlying shape. But we must stay within what the data allows. The cosmic background glow is our best tool for detecting global curvature. Its temperature variations reveal the geometry of space. These variations suggest that the universe is very close to flat. They do not demand that it is infinite. They only tell us that if space curves, the curvature is too gentle to detect at the scale we can see. This gives rise to a quiet irony. Space may be curved enough to loop, yet the loop may be so large that no light in the history of the cosmos has had time to reveal it. A universe that loops in 30 or 50 billion light-years could still appear flat inside your light cage. The loop would be real, but invisible. Consider again the foggy maze. Your vision ends before the path closes. You trace straight lines that hide the loop. If you lived your entire life inside the fog, the idea of a global loop might seem impossible, yet the loop exists, the maze has a shape, the fog only hides it. Now return to the watchtower. The watcher stands high above the island, searching for patterns that might repeat across the sky. The watcher compares patches of the cosmic glow, looking for matching patterns that would reveal a loop. The watcher scans the positions of galaxies, looking for duplicates. The watcher listens for echo-like signals. So far, the sky remains silent. No repetitions appear, no loops reveal themselves. But the absence of evidence is not evidence of absence. The watcher knows that the silence might mean the loop lies beyond reach. The watcher knows that a nearly flat region can still belong to a curved hole. The watcher knows that the true shape of space may lie just outside the bubble of light that surrounds the island. This brings us to a final question. If space might loop, why have we not seen any sign of it? The answer lies in the limits of time. Light has traveled only a finite distance since the beginning. The universe may have loops that lie beyond that distance. Until more time passes, or until new methods find indirect clues, the loops remain hidden. This is why the global shape of space is one of the deepest mysteries of cosmology. It sits just beyond the reach of measurement. It shapes everything, yet it reveals almost nothing. It invites speculation while demanding caution. It reminds us that our place in the universe is defined by what we can see and by what we cannot. In the next chapter, we will test the edges of possibility and ask whether bridges through space-time, even theoretical ones, can reveal anything about the unreachable regions beyond our light cage. Stand again at the top of the watchtower, this time not to observe, but to imagine. For centuries, you have mapped the sky with the tools nature allowed, staring outward through the narrowing keyhole of the visible universe. But at some point, the question grows louder. If the cosmos hides vast regions behind unreachable horizons, can experiment ever reveal anything about them? Is there any way, even in principle, to probe the edges of space-time itself? This chapter steps into that strange territory where physics meets imagination, not to abandon evidence, but to test its limits. Begin by grounding the scene. Experiments in cosmology do not happen in laboratories alone. They happen in the motions of galaxies, in the timing of pulsars, in the ripples of gravitational waves, and in the faint afterglow of the early universe. These signals are your instruments. They arrive from the edge of your light cage, carrying messages about conditions you cannot reproduce on Earth. When you measure them, you are performing experiments with the universe as the apparatus. Now acknowledge a simple fact. If your horizon is a boundary of information, and if expansion continues to push distant regions beyond reach, then no telescope, no matter how advanced, will let you see everything. The edge is real. It is a line you cannot cross by observation alone. Yet physics does not stop at that line. When direct measurement ends, inference begins. To test space-time, you must push your methods to the razor-thin border between what is measurable and what is only guessable. One path begins with gravity. Gravity curves space-time. If space-time contains hidden structures or unreachable regions, gravity may hint at their influence. The idea is subtle. You cannot see beyond the horizon, but mass beyond your view could still affect the curvature inside your view. If you map gravitational lensing with extreme precision, you might detect small distortions that do not match the visible matter. Most of these distortions come from matter you cannot see locally. But in principle, a tiny contribution could arise from the global shape of space beyond your reach. This method is indirect. It cannot reveal what lies outside the cage, but it can constrain possibilities. The edge of everything leaves a fingerprint in the bending of light. A second path runs through gravitational waves. These waves carry information about events that shake space-time itself. They travel across the cosmos with remarkable stability. If space-time contains subtle defects, loops, or exotic structures, gravitational waves might pick up slight distortions during their journey. These distortions would be tiny, almost impossible to detect, but not entirely out of reach. In principle, a network of extremely sensitive detectors could map the structure of spacetime in 3 dimensions, not just through light, but through the trembling of spacetime itself. A third path comes from particle physics. Some theories propose that spacetime has additional layers or hidden dimensions. These dimensions would influence the behavior of particles at high energies. If such dimensions exist, they would not allow travel beyond the horizon, but they might allow interactions that give the horizon new meaning. An experiment performed in an underground accelerator could reveal clues about the deeper architecture of spacetime. In this sense, the edge is not merely a boundary of distance. It is a boundary of structure. So far, these paths remain grounded in measurable reality, but now step closer to the line where speculation and physics meet. For decades, theorists have proposed ways to break through the limits imposed by ordinary spacetime. They imagine shortcuts and tunnels, bridges between distant regions. They describe warped paths, curved surfaces, and exotic matter that bends geometry enough to fold distant points together. These are not engineering plans. They are mathematical tests of what spacetime allows when pushed to its extremes. One such idea is the concept of a traversable wormhole. In the equations of general relativity, certain solutions allow 2 distant regions of space to connect via a tunnel-like structure. If such a tunnel exists, it could theoretically allow travel from one region to another without crossing the intervening space. But these solutions require exotic forms of matter with negative energy densities, something never observed in nature. Without such matter, the wormhole collapses before anything can pass through. It is a door that slams shut the moment you try to open it. In everyday language, you can think of a wormhole as a fragile pane of glass suspended in the dark. Touch it with even a gentle force and it shatters instantly. The equations allow the pane to exist, but the moment you try to use it, the pane breaks. The barrier is not technical, it is structural. The universe protects its causal boundaries. Another idea is the warp bubble. In theory, spacetime could expand behind a region and contract in front of it, moving the region faster than light relative to distant observers without violating local speed limits. This concept also requires exotic energy. Without it, the bubble cannot form, and even if it could form, calculations suggest it would create horizons of its own, trapping anything inside. The bubble becomes a cage, not a vehicle. These ideas lead to a deeper question. Why does spacetime appear to resist every attempt to form shortcuts? If the universe was once capable of rapid expansion, why can that expansion not be controlled? If spacetime can bend to form black holes, why can it not bend to form stable tunnels? Perhaps the answer lies in the structure of energy. Perhaps the early burst of expansion was driven by a field that no longer exists. Perhaps nature allows certain geometries only under extreme conditions that cannot be reproduced. But there is another possibility. Perhaps the universe protects its causal boundaries for a reason. If horizons exist because of rapid expansion, then shortcuts would undermine those horizons. If the cosmos contains unreachable regions, then instruments capable of connecting them would violate the structure shaped by the early expansion. Maybe the universe prevents certain configurations because they conflict with deeper principles. This is not mysticism. It is a recognition that physical laws may enforce global constraints. Now bring the discussion back to observation. Even if wormholes and warp bubbles remain mathematical shadows, the attempt to build them is itself an experiment. The question is not whether they can be engineered. The question is whether the laws of nature allow them at all. If the laws forbid every known shortcut, that itself is evidence about the structure beyond the horizon. It suggests that the horizon is not merely an observational limit but a fundamental feature of the cosmos. Consider a human-scale analogy. Imagine standing in a room with one locked door. You try to pick the lock, it resists. You try a crowbar. The hinges do not budge. You try to cut through the wall, but the material is harder than steel. At some point, you realize the room was designed never to open. Its architecture enforces the limit. The locked door is not an invitation to escape. It is a signal that the room is complete as it is. Experiments at the horizon operate in the same spirit. You test every path, and every path leads back to the same conclusion. The horizon is not a wall, but a limit woven into the structure of space-time. It cannot be crossed. It cannot be pierced. It cannot be bypassed. Not because the machinery is insufficient, but because the universe is consistent. Why does this matter? It matters because the horizon defines what the universe can reveal. It matters because science depends on the flow of information. It matters because if the universe protects its causal structure, then everything we call real must exist within that structure. It matters because limits are as informative as discoveries. A horizon that holds firm tells you something deep about the nature of space-time. Now return to the watchtower. The watcher stands at the highest floor, surrounded by instruments that reach as far as physics allows. The watcher sends out signals. They fade. The watcher listens for echoes. None return. The watcher bends light and gravity to probe the darkness. The darkness bends back, but never breaks. The watcher tries to imagine shortcuts through the night. The shortcuts dissolve. And yet, the watcher is not defeated, for in every limit, there is direction. If wormholes collapse, that tells you something. If warp bubbles trap themselves, that tells you something. If gravitational waves arrive unwarped, that tells you something. If the horizon holds, that tells you something. Every failed attempt is a piece of evidence. Every boundary is a clue. The universe reveals itself by the ways it refuses to be forced. In the next chapter, we will step beyond speculation and ask what lies outside our bubble of reality, not through travel, but through the patterns left behind in the light that still reaches us. Stand once more atop the watchtower, but now let your eyes drift beyond the familiar darkness. The galaxies that once filled the sky have thinned. The earliest starlight has faded. The horizon shaped by expansion now wraps around your world like a quiet boundary. You have traced its structure, measured its limits, and pressed against its silence. Now a harder question emerges. If the universe beyond this boundary exists, what kind of place is it? What lies outside our bubble of reality? Begin with what the sky tells you plainly. The observable universe is not the entire cosmos. It is only the part that has had time to send its light to your island. You see a sphere of galaxies 46 billion light-years in radius. Outside that sphere, space continues. It does not end. It does not thin. It does not fade into nothing. But every region beyond the edge is unreachable. Their signals will never reach you. The universe extends, but your access does not. This is the first step toward the idea of a larger structure. Your bubble is not the cosmos. It is only your domain of communication. It is a local room in a far larger building. That building may be simple. It may be infinite. It may be layered. It may be fragmented. You do not know, but you can infer possibilities from the clues inside the bubble. Begin with the most cautious possibility. The cosmos might be uniform, smooth, and infinite. In this picture, the regions you cannot see look much like the ones you can. Their galaxies follow similar patterns. Their laws of physics match yours. Their structures are simply too far away for their light to reach you. If this is true, then the bubble of reality is an accident of time. Outside the bubble lies more of the same. But another possibility is more intriguing. The cosmos may be uniform only in your region, far beyond your horizon. Conditions could be different. Perhaps the density of matter varies. Perhaps the laws of physics shift slightly. Perhaps the shape of space changes. If rapid expansion once acted unevenly, then the early universe may have formed domains with different internal rules. Your bubble could be one domain among many. Now entertain the possibility that the cosmos contains many such domains, each a bubble separated from the others by regions that expanded too fast for signals to cross. In this view, the universe is a collection of isolated islands. Each island has its own internal history, shaped by the conditions within it. The islands do not collide. They drift apart as space grows between them. From inside any island, the others remain invisible. Imagine a vast library shrouded in weak light. Shelf after shelf stretches beyond sight. Each shelf holds books in different languages, written in different styles. You occupy one room of this library. You can read the books on your shelf. You can sense faint vibrations from shelves beyond. But the other rooms remain unreachable. The universe might be this shadow library, a collection of regions, each with its own narrative. If this picture holds, then your bubble is one page of a larger book. You cannot read the other pages. You cannot know the larger story. Yet the existence of other pages shapes the meaning of your own. You do not live in a solitary cosmos. You live in one version of reality, defined by the rules that shaped your region after rapid expansion. This brings us to the boldest possibility, one that has been proposed not as fantasy, but as a mathematical consequence of certain models. If the early expansion continued in distant regions, forming endless islands of reality, then your universe is one bubble in a sea of bubbles. Some bubbles may be empty. Some may be filled with exotic structures. Some may resemble yours closely. Some may differ in profound ways. You will never see them, but they may exist nonetheless. At this point, we must pause and separate what is supported from what is speculative. The existence of other domains is not directly observable. It is an inference drawn from how the early universe behaved in your region. The mathematics suggests it. The sky does not confirm it. Yet the idea persists because it helps explain several puzzles, including why the observable universe is so uniform and why the laws of physics appear finely balanced for the formation of structure. Now ask a deeper question. If there are many domains, what determines their properties? One answer lies in the initial conditions of rapid expansion. Slight variations in the early energy field could freeze into different configurations. Each configuration would shape the physics of its domain. Your bubble could be one outcome of a cosmic process that creates many possible worlds. In this view, your observable universe is not the whole story. It is one instance of a general pattern. But there is an even stranger possibility. Some theories suggest that the fabric of reality is not fundamental. Instead, it may be emergent. According to this idea, the three-dimensional world you experience is like an image projected from a deeper surface. Information stored on a boundary could encode everything inside. This idea has roots in studies of black hole physics, where the amount of information a black hole can contain appears proportional to its surface area, not its volume. If this principle extends to the cosmos, then everything you see, every galaxy, every cluster, every particle, might be encoded on a distant surface. The universe would not be a volume but a projection. You would be living inside a hologram, not in the sense of illusion, but in the sense of structure. Reality would be real, but organized in a way that defies everyday intuition. Outside your bubble of reality would not be more space. It would be the deeper surface that encodes everything you can observe. This idea does not imply that the universe is simulated. It does not require artificial design. It only suggests that the deepest layer of physics may look nothing like the world it produces. Space, time, and matter could emerge from patterns on a boundary much larger than your visible region. You would be observing the three-dimensional shadow of a higher-order system. This leads to a subtle and unsettling question. If reality is encoded on a distant boundary, what lies beyond that boundary? Is there a deeper layer? Does the cosmos contain a hierarchy of structures? Are you living in the interior of a single layer, or are you part of a sequence that extends indefinitely? If the bubble you see is only a projection, how many layers of projection lie above it? Now we come to the biggest reveal of this chapter, one that transforms the meaning of the visible universe. Every clue we have suggests that our cosmic bubble is not the whole of reality. The early expansion created regions forever cut off from one another. The patterns of the background glow hint at structures beyond our reach. The mathematics of gravitational fields suggest deeper layers of encoding. The universe you observe may be a fragment of a larger architecture, a local window onto something far more expansive than your instruments can detect. If this evidence-driven view expands your sense of reality, please like and subscribe to the Quiet Universe channel. Let this sink in slowly. You are living inside a domain shaped by initial conditions you cannot witness, ruled by laws that might not hold elsewhere, bounded by horizons you will never cross. You are reading one chapter of a story whose other chapters you cannot access. The silence beyond the bubble is not empty. It is simply beyond reach. Bring this back to human scale. Imagine living in a valley surrounded by mountain ranges so tall that no signal can cross them. You know your valley intimately. You map its rivers, its forests, its farms, but you do not know what lies beyond the ridges. Other valleys may exist. They may be similar or strange. You cannot see them, but their existence changes how you understand your own place. You are not the center of the world. You are the inhabitant of one valley among many. This realization gives the quiet horizon new meaning. It is not a dead end. It is a boundary between what is accessible and what is not. The cosmos invites humility. It invites inference. It invites imagination grounded in the clues written across your sky. You may never see beyond your bubble, but the bubble itself carries traces of a deeper structure. In the next chapter, we will draw the final map our instruments allow, tracing the possible endings of the cosmos and asking what meaning remains when the universe approaches its last horizon. Return to the watchtower one last time. The sky around you has thinned. Structures that once filled your maps have slipped across the future horizon. The earliest starlight has been gathered. The ripples from the primordial burst have been charted. The clues written into gravity, light, and geometry have been extracted. Now you face a quieter task. You must take everything the universe still allows you to see and draw the final map. Not of space alone, but of the possible futures that await the cosmos. This last chapter of Act 2 is about the endings encoded in the sky, the long arcs of time that stretch far beyond the lifespan of stars, and the faint traces that hint at what remains when the universe grows old. Begin with the simplest observation. The universe is expanding. The galaxies you mapped in earlier chapters drift apart. The expansion is accelerating. This acceleration is not subtle. It dominates the long-term fate of everything. If it continues, the cosmos will not collapse. It will not cycle back on itself. It will fade. Stars will burn out. Galaxies will disperse. The universe will approach a state where energy is too thin to build or sustain structure. This is the scenario known as heat death, the quietly chilling possibility that awaits a cosmos ruled by acceleration. Imagine the universe in this distant future. The bright clusters you know today become faint traces. Stars consume their fuel and cool into embers. Black holes grow for a time by capturing the wreckage of their surroundings, then slowly evaporate through quantum processes. The temperature of space approaches absolute zero. Nothing changes on cosmic scales. Time still flows. But the events that once gave time meaning have ended. The universe becomes a vast, dark sea with no storms left to stir it. This is one possible ending, but not the only one. Different maps exist depending on the underlying rules. If the energy driving the acceleration changes sign or weakens, the expansion may slow. If it reverses, the cosmos could turn inward. Galaxies would approach one another. The sky would brighten with collisions. The universe could collapse into a final fireball, squeezing matter and energy into a dense point. This is the Big Crunch, a mirror of the beginning. It is dramatic, violent, and speculative. Nothing in the current data demands it, but the possibility exists if the forces at work today evolve differently. A third map exists for an even more radical ending. If the acceleration grows stronger over time, the expansion will not merely separate galaxies. It will break the bonds of gravity within galaxies. It will tear apart solar systems. It will stretch planets. It will unravel molecules. In the extreme scenario known as the Big Rip, the fabric of space-time accelerates so violently that even atoms cannot remain intact. This scenario is not favored by the evidence, but it reveals how the pace of expansion decides the final shape of reality. To understand these maps, step into a human-scale analogy. Imagine a great canvas stretching across a frame. If the frame expands gently, the canvas thins but remains intact. If the frame expands faster, the canvas stretches and may tear. If the frame contracts, the canvas wrinkles and bunches. The universe behaves somewhat like this canvas, shaped by the tension between expansion and gravity. The future of the cosmos depends on which force wins across billions of years. Now look at the evidence you already have. You see galaxies receding at speeds proportional to their distance. You see the brightness of supernovae altered by expansion. You see the cosmic background glow stretched into microwaves. All these clues suggest that the expansion is not slowing. They suggest that acceleration will continue, at least for a very long time. The most conservative map therefore points toward a quiet ending, a universe that cools, empties, and fades. This is not a dramatic finale. It is a slow, patient descent into stillness. But even this simple ending contains layers of mystery. In a universe that cools indefinitely, rare events may still occur. Quantum fluctuations could create temporary pockets of order. Entire particles might appear from empty space and vanish over inconceivably long timescales. It is possible that new structures could arise spontaneously. These structures would not change the overall fate. They would flicker and disappear. But their existence raises a strange question. Can a universe that is mostly still host small, improbable sparks? And if so, what meaning do those sparks hold? There is another map to draw, one that deals not with endings in time, but with endings in information. Your light cage defines the visible cosmos. As expansion continues, that cage will shrink in content. The galaxies you can see today will fade. Eventually, only your local cluster will remain visible. After that, even local structures will change. The sky will not merely grow dark, it will lose the data needed to reconstruct the story of the universe. Future astronomers, if any survive the long descent, will be unable to learn the true history of cosmic evolution. They will see only a small pocket of matter in a dark, empty void. Their map will be smaller and more misleading than yours. This raises a deeper theme. The universe changes not only in structure, but in knowability. The past becomes sealed. The early chapters become invisible. The evidence you rely upon now is temporary. You live in a privileged era, a moment when the cosmic web is visible, when the afterglow of the early universe still reaches you, when the structures needed to understand the universe's birth are still intact. In the deep future, that privilege will vanish. The map you draw now will be the final one. No future mind will redraw it with more accuracy. Now turn to the more speculative edges of the final map. If the cosmos contains other domains, as explored in the last chapter, then the ending you draw applies only to your bubble. Other bubbles might expand differently. Their laws might permit different endings. Some might collapse. Some might fragment. Some might drift into deeper layers of structure. Your map is local. It is complete only for the region you inhabit. This suggests a quiet reversal in perspective. You began by assuming that the universe is one thing. Now you are forced to admit that your universe may be one instance. Its ending may be one of many. The map you draw is not a grand atlas. It is a local chart. Beyond your horizon lies an unknown world whose fates may differ. Still, the absence of certainty does not erase meaning. Even incomplete maps can reveal truth. The patterns you observe suggest that the cosmos evolves, cools, and stretches. The sky carries the echoes of its origin. The loss of those echoes in the future tells you that the universe has a direction. It has an arrow of time. It moves from ordered states to disordered ones, from bright skies to empty ones. This flow gives the cosmos structure, even if its ultimate fate remains uncertain. Now bring this down to a final human-scale image. Imagine a long corridor with lamps spaced far apart. At the beginning of the corridor, the lamps shine brightly. As you walk, each lamp grows dimmer until only the nearest one provides any light. Eventually, even that lamp fades. You continue walking in total darkness, guided only by memory. The universe is that corridor. The bright lamps represent the early epochs. The dim lamps are the structures you see today. The future is the darkness beyond. Why does this matter? It matters because the final map you draw will shape the way you understand your place in time. It matters because the fate of the cosmos influences how you interpret its origin. It matters because knowing the possible endings gives context to the middle chapters. It matters because the universe is not static. It is a story. And every story has an arc. At the end of this chapter, you stand with a map that is both rich and incomplete. It shows how the cosmos expands. It shows how galaxies drift. It shows how light fades. It shows how horizons form. It shows how information dies. It does not show what lies beyond your bubble. It does not show what came before the earliest light. It does not show what deeper structure reality holds. Yet it is the final map we can draw with the tools the universe allows. In the next act, we will turn from measurement to meaning and ask what our fragile moment in this vast story tells us about existence itself. Stand once more at the top of the watchtower, but this time do not measure anything. Let the instruments rest. Let the graphs and the maps and the distances fade to the edges of your mind. For the first time in this long ascent, you are not here to observe the universe. You are here to face the quiet weight of what the universe has shown you. Around you stretches a sky you now understand in a way no ancient observer ever could. You know why galaxies drift. You know why the first starlight arrives as a whisper. You know why the horizon wraps itself around your world like a moving veil. You know that the observable sphere is not the cosmos, but a temporary window carved by time and light. You know that the universe has a beginning, and you know that its endings branch into futures you can sketch but never confirm. Yet with all this knowledge, a deeper question stands in the cool air of the watchtower. What does it mean to exist in a universe that hides almost everything? What does it mean to be a species whose instruments can measure billions of years into the past, but whose own presence spans the briefest instant? What does it mean to live inside a bubble of light, aware that the true structure may be far larger than any map you can draw? Begin with the paradox that has been building since Act 1. You are a conscious observer inside a universe that limits what you can observe. You peer outward through a cage of light. Everything you know, everything you can test, everything that can enter your mind as data must pass through that cage. But your thoughts, your questions, your hopes, and your fears extend far beyond it. Your imagination outruns your horizon. In this, you mirror the universe itself, which once outran its own causal boundaries. In everyday language, you can think of your cosmic position as a room whose walls move. The walls are not made of stone. They are made of time. As time flows, the walls expand. More of the universe becomes visible, but only to a point. Then the walls stabilize. Beyond them lies silence. The silence is not empty. It is simply unreachable. Your life unfolds in that room. Your discoveries happen inside that room. Every meaning you create must be grounded in what the room allows. Now pause and let a deeper question rise. If the universe limits what you can know, does it also limit what you can mean? Does the inability to see the whole cosmos diminish the significance of your existence? Does the vastness of the universe dwarf the value of a single life? Or does that life draw its value from within, shaped not by scale, but by awareness? Step down from the tower for a moment and consider a human scene. Imagine a child holding a flashlight in a dark field. The beam lights only a small circle of grass, leaving the rest of the field unseen. Yet within that circle, the child builds a world. They invent stories. They explore. They learn. The vast darkness outside the beam does not remove meaning from the small illuminated patch. Instead, it gives the patch a frame. It makes every flicker of light precious. Your bubble of reality works in the same way. It illuminates one region of a far greater whole. The darkness beyond does not erase the value of what you can see. It sharpens it. It makes every measurement a moment of connection between your brief existence and the ancient structure that surrounds you. Meaning does not come from the size of the cosmos. It comes from the fact that the cosmos produces minds capable of asking what it means. Now consider the future of that bubble. In time, the sky will thin, the galaxies will fade, the early glow will vanish, the cosmic web will dissolve from visible memory. If intelligence survives into that distant era, it will live under an empty sky. It will not know what you know. It will not see what you see. It will build its own picture of the universe, smaller and more constrained than yours. To that future intelligence, the cosmos may appear static and solitary. This fact reveals something profound. Knowledge has seasons. You live in a season of abundance. The sky is full. The evidence is rich. You are able to reconstruct the universe's story because you exist at a time when the universe is still telling it. This is not an accident you can take lightly. It is a responsibility. The map you draw today may be the only map the cosmos ever offers. When the sky slips away, this era will become the archive of cosmic memory. So what should you do with this knowledge? Should it make you feel small? Should it make you feel temporary? Should it make your questions seem insignificant compared to the scale of the universe? Or should it inspire the opposite? A recognition that meaning arises not from how much of the universe you can touch, but from how deeply you can understand the part you inhabit. Here a quote whispers through the quiet air, a reminder distilled from every instrument ever lifted to the sky. The universe may not care that it once held creatures who could think, but that does not diminish the reality of the thoughts themselves. Existence is real because it is experienced. Meaning exists because minds arise to create it. The cosmos does not need intention to produce significance. Significance emerges whenever awareness encounters mystery. Now return to the watchtower for the final time. You stand within a shrinking sphere of accessible information. You know the universe may be infinite in extent. You know it may contain structures far beyond what you can ever observe. You know that your life, compared to cosmic time, is a flicker. Yet you also know that without observers like you, the universe would remain silent. It would contain structure, but not story. It would contain motion, but not interpretation. It would contain beauty, but no eyes to see it. This realization reframes your understanding of the cosmic horizon. It is not a limit imposed on you. It is the shape of the universe's invitation. It draws a boundary not to confine thought, but to focus it. You cannot know everything, but you can know something deeply. You can trace the patterns of matter. You can measure the glow of the early universe. You can infer the structure of space. You can imagine what lies beyond your bubble without claiming certainty. This balance of knowledge and humility is the heart of the human place in the cosmos. As the night deepens around the watchtower, the final image comes into view, a lone photon, traveling across billions of years, crosses the boundary of your bubble and touches your world. It is a traveler from a time when the universe was young. It has no intention. It carries no message. Yet when it arrives, an image forms. A pattern emerges. A measurement becomes possible. And in that moment, the universe knows itself through you. So the question that remains, the question that closes this long ascent, is not about what lies beyond the horizon. It is about what you will do with the light that still reaches you. And as the final echo of this act settles into the silence, one question lingers in the air. If the universe can only ask its deepest questions through the minds it creates, then what question is it asking through you now?